Good evening, class. Let's see here. Is Vic Pham here? Not here? Danny Mendes, I thought I checked him in.
Yeah.
Danny, are you here?
Hello.
Yeah, I thought I checked you in. Okay. All right. Thank you. Deepika, not here. Nicholas Kenny. No. How about Eric Andes? Not here. Yeah, I keep telling students I need to see a profile picture in order to let them come in, but they still don't do that for me. Okay, so I hope you noticed that I just uploaded some more lecture notes, okay, on Canvas. All right, so my plan for today is to lecture sections 4.1, 4.2, and then I like to save some time to go over the quizzes for you because the test is going to be on Wednesday. Okay, so just in case you have any questions, then you can ask. Okay, so let me share the screen to see what we have. Okay, so this is what we have. Okay, yeah, let me see this. Okay, so we're gonna do 4.1, 4.2, unless you have any questions from section 3.2 and 3.3. Do you have any questions from those two sections? No? Okay, so let me see. Is Andrew Kang here? Andrew Kang is not here?
I'm here.
Oh, okay. Thank you. I'm glad I always double check before I mark a student absent. All right. So if you don't have any questions from 3.2 and 3.3, then let's get started on 4.1. Now, as you can see, there is a lot of writing in section 4.1. Okay. So I try to write as much information as possible so you can read, but please be sure to read the book also. Okay. In the past, I never provided past lecture notes except just the objectives. So basically, when student comes to class, I just write these on the board. Okay. But then if they are long, then I just email them. In that way, it's easier for me to teach because I have freedom of writing any way I like, right? Okay. When I provide past lecture notes like this, so it's a more structured way. So I have to write exactly where it's supposed to be written, and so on. So it's harder for me to teach that way because I like to write a lot, and when I do this, then it's a lot of work for me because I have to prepare this stuff, but once everything is done, then it's easy. But in the beginning, it takes a long time to prepare the lecture notes like this. Okay, but anyway, but I cannot cover everything in the section, so please always read the book. All right, so let's get started. So in here, we're gonna learn some new vocabulary, okay, and the terminology that you need to be familiar with. So later on, when I mention something, then you know exactly what I'm talking about, okay? So let's talk about, especially in this chapter, we're going to talk about homogeneous equations and non-homogeneous equations, all right? Okay, so let's start from the beginning. All right, so here again, you have seen this, okay? This is the general differential equation of nth order, okay? So that is the linear nth order differential equation, okay, like this. And remember, when we divide, we divide the initial, the leading coefficient to both sides, then that would give you the differential equation in standard form, right? Or if you get the y, the nth derivative of y by itself, then that is the normal form. Okay, so we've learned all of those. Okay, so now, so I give you this general differential equation. Okay, now if you replace the g of x with 0, that means if the right hand side is 0, then that resulting equation, we call it the associated homogeneous differential equation of this general differential equation, okay? So any differential equation has an associated homogeneous differential equation. So you need to know that. And the associated homogeneous differential equation is when the right-hand side is 0. Okay, so it's important for you to know the terminology, differential equation, a homogeneous differential equation, okay? And that is when the right-hand side is 0, okay? So let me highlight that also so you can see. So that is on the right-hand, so especially the right-hand side. So I'm gonna emphasize that, okay? Now, the next one is called the non-homogeneous differential equation of this given differential equation, okay? Do you see there is any difference between this one and that one? Are there any differences?
No.
No, right? Okay. So why are we calling this one a new name? Well, let's highlight this. So when the right-hand side is non-zero, then we call that differential equation a non-homogeneous differential equation, okay? So in general, a differential equation of any order, okay, has two parts. One, when the right-hand side is 0, then we call that the homogeneous differential equation of the given differential equation, okay? And the differential equation by itself, like the given one, where the right-hand side is non-zero, we call that a non-homogeneous differential equation, all right? So star, which is this given differential equation, has two parts. It has a homogeneous differential equation and it has a non-homogeneous differential equation. So when you are asked to solve a differential equation, of course, like from here, from the second order on up, it's harder to do. If it's a first order, you learned all of the methods in chapter 2 already. So when the order is second or higher, and you're asked to solve a differential equation, or in general, that is actually a non-homogeneous differential equation. You can call it that way, okay? Because they are the same, right? Okay, so if I ask you to solve a non-homogeneous differential equation, that non-homogeneous differential equation has two parts, and that are, again, the homogeneous equation or the associated homogeneous differential equation and the non-homogeneous differential equation itself. So to solve this differential equation, you have to solve this homogeneous differential equation and also this non-homogeneous differential equation. So let's say y sub c is the solution of this homogeneous differential equation. Okay, we write c because y sub c means the complementary. Okay, so this y sub c is the complementary. Or some textbook call it the homogeneous because it is the solution of the homogeneous differential equation, right? Solution. Okay. And y sub p, we call it the particular solution. Okay. So here you have a complementary solution. So you need to know what that means. Okay. And you also need to know what a particular solution means. Yeah, we talked about particular solution back in chapter 2, but that's different. In chapter 2, when I gave you a differential equation and you solve, and the general solution contains a constant c, then we call it a general solution. But if I give you a condition, which is like an IVP, okay, an initial value problem, you plug the condition in to find the c, then the resulting solution is called a particular solution. Okay, in this case, it is different. Okay, it is different. This particular solution is just the solution of the homogeneous differential equation. That's all. The non-homogeneous differential equation. All right. So if you want to solve this differential equation right here, then that means you want to find the general solution of this. And the general solution of this differential equation is equal to the complementary solution that you got from the associated homogeneous differential equation, okay, plus the particular solution that you got from the non-homogeneous differential equation. Okay, do all of you understand? And I'll get this. So from now on, when I give you a higher order differential equation and I ask you to solve, if that differential equation is a non-homogeneous differential equation, in other words, the right-hand side is not a zero, then you have to find the complementary solution and also the particular solution of that differential equation and add them up to get the general solution. Okay. So the general solution is this. All right. So I'm just repeating. Okay. So where y sub c, so where y sub c is the complementary solution of the associated homogeneous, okay, the associated homogeneous differential equation of that differential equation. Okay. Okay. That means, and you can just write, you can just, that is a sub n of x, y, and derivative a sub n minus 1 of x, y to the n minus first order, and you just do dot dot dot, and then a sub 2 of x, y sub y double prime plus. You don't have to write everything here because then you can save time. Okay, so it's just a way. So you need to know how to take notes, but I'm writing all of this down so you can see. Okay, but you can just write, basically just write the first term, right? You write the first term and they go dot, 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 and then the last term, then you know that it meant some this guy up here because I already wrote it up here, you see? Or you can just give it a name and you just write down. So, you know, you just need to know how to take notes to save time, okay? Now, and what about y sub p? So y sub p is the particular solution of the non-homogeneous differential equation of the non-homogeneous differential equation, okay? So here, just write a sub n x y, the nth derivative, and you just go dot, dot, dot. And then if you want to, you can just write two terms here. So you, and then equals g of x. All right. Okay, so this part right here that which I just talked about is very important. All right. So from now on, anytime you solve it a higher order differential equation, make sure you find a y sub c and y sub p. If your given differential equation is a non-homogeneous differential equation, okay, so this is called a non-homogeneous because the right side is not zero. All right. So you're going to see some of the stuff here that I talked about in chapter 1, and I'm repeating here in this section. So differential operator. So what is a differential operator? So there, you know, like if you have like the derivative of y with respect to x, we can call it a d, right? We can use the capital D. So capital D here, that's why we don't use capital D as a constant, okay? Because capital D is a differential operator. So avoid using capital D as a constant. So it's called differential operator. All right. Okay, so that is a differential operator. Okay, so since this is a differential operator, then I'm rewriting the non-homogeneous differential equation from the first line right here. Okay, right here. So now instead of the nth derivative of y, I rewrite that as d to the nth power. So you need to know that d to the nth power means the nth derivative of y. Okay, so that's what it means. Okay, and then right here, instead of the n minus first derivative, it is written like this. So you do that for all of the derivatives. So until here, this is y prime, which is d. Y double prime is d squared. And there's no derivative here, so you just rewrite that, right? So you see that all of these right here have a y in common. So in a way, okay, so listen to this carefully. We say informally, all right? Informally, we say we factor y out, but we are not actually factor. Y is not a factor because these are all derivatives of y, okay? So informally, you can say, I'm going to factor y out, but it is not a factor actually, okay? So I do that because basically what this one means is when you have this whole thing right here operate on y, that means each term is operating on y. So each term, like this is the nth derivative operator, operates on y, and then the n minus first derivative operate on y, and you do that until you get to the last term, okay? So all of these right here. So let's highlight all of these. Okay. We just hate to keep writing this because it's too long, right? So we try to rewrite that in a shortcut way. So we say everything there, we're gonna write that as L, okay? So L is a differential operator operating on Y. Okay, you'll just see how short that is. Yeah, so it's much nicer, right? So that's the same thing. So instead of So right here, if you have like the first derivative of y, we write it as dy. So d is a differential operator. This L right here is also called a differential operator, and it is this expression right here. All right. So where I'm just repeating again. So where L. So when you see 3 lines like this, instead of 2 lines for an equal sign, that means L is defined to be. Okay, that's what it means. L is defined to be this expression right here. No, not. So when you use the D operator, you don't put parentheses around the order of the derivative. Okay. N minus 1 plus dot 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 plus a1 of x dy plus a sub 0 of x. That's it. Okay. So that's what it is. If you want to, you can just put brackets around, so you know that the whole thing there is an L operator, and I'm gonna highlight that again. Okay. Which is called a differential. Should I skip it to the next line? Okay, it's easier for you to read. A differential operator. I think my handwriting looks nicer when I use my app, iPad Pro. Okay, I don't like the handwriting here. All right, so let's look at this example. So example 1. So that is written in the normal form, in the regular way of writing a differential equation. Okay, so let's try to use a differential operator for this one. Okay, so basically that's all. I'm not asking to solve. So I say so. This is d cubed, right? Y plus 3d squared. So you need to know how to use the d operator here to rewrite a given differential equation. Okay. So, and then you can do this. Okay. So that means what is L? So L in this case is this differential operator right here. Okay. I should have said like maybe right here you say, I say find L. Okay. Do that. All right, in this case right here, by looking at this differential equation, can you tell me a solution of y? Can you guess by observation? Look at this one and tell me what you think y is. Any guess?
Y equals 0.
Okay, why? Because when you plug in 0 for y, the left-hand side is 0, agree?
Yeah.
Okay, so y equals 0 is a solution. What is the name of that solution, remember? Do you remember? When the solution is y is 0?
Would that be trivial?
Yes, trivial solution. Okay, so y equals 0 is a solution for all x in this case, right? Because it works for any x value. Okay, so if y is equal to 0, if y equals 0 is a solution of a differential equation, we call that a trivial solution. Okay. A trivial solution is easy to find. So whenever I ask to solve a differential equation, don't say the solution is y equals 0, okay? And not all differential equations have a trivial solution. So when we actually want to solve a differential equation, we want to find a non-trivial solution, because a trivial solution is very easy to find. Agree? You can just let y be 0 and check to see if the left-hand side is equal to the right-hand side. If it is, then y equals 0 is a trivial solution, okay? All right, now let's talk about linearity property of the L operator, okay? So what does it mean? Remember, like a derivative has this property. An integral has this property. A limit has this property. Remember in calculus 1, when I gave you the limit of a sum of two functions, you can just take the limit of the first function plus the limit of the second function, right? Same thing for a difference for a derivative. You take the if I give you the derivative of a sum, you can just take the derivative of each function and then add them up. Or when you take the derivative of a constant times the function, you can just pull the constant outside and then you multiply by the derivative of the function. So you know that derivative has linearity property, integral also has this property, limit also has this property. Now the question is, does this differential operator has the same property? And yes, it does, because this differential operator is actually derivatives, right? It's just a combination of derivatives. Since the derivatives have these properties right here, then so does this one, okay? And we call that the linearity property, and it has two parts. Part number one, it says the linear operator operates on a sum of two functions, then the property allows you to take the linear operator and operate on the first function and then add a 2, and then you take the operator and operate on the second function, okay? Or when you have a constant times the function, then, and when you operate that on a constant times the function, you can pull out the constant and then you multiply by the operator on the function, okay? Now, these two can be combined into one line, and that is like this. So it says if you operate on a sum of two functions that are multiplied by two coefficients, like alpha and beta, okay, then that can be factored out, and then you operate on y1, and then for the second one, you factor out the constant beta, and then you operate on y2, okay? Where alpha and, let me write, alpha and beta are constants. All right. So with that said, then let's go back to the given differential equation from the beginning, okay, which is the star. Uh-oh, my OneNote. Do you see it's just not responding? Okay, what's going on? Okay, everything is fine. So that is the differential equation that we have from the beginning, which is this guy. So that is this one, right? Now, so we can just summarize everything. So if the right-hand side is 0, then we have this. And what do we call this equation right here? What do we call it when the right side is 0?
Trivial solution.
No, we call it a
associated homogeneous?
Okay, yes, or we can just simply call it a homogeneous differential equation, which is associated with this equation right here, but we just call it a homogeneous differential equation. Okay, now if the right hand side is not zero, okay, so right here, if the right hand side is zero, you call it that. If the right hand side is not zero, that means it is some function of the independent variable, then we call it a non-homogeneous okay. I remember like in the past when I taught this section, I just constantly wrote on the board, right, on my laptop, and just wrote and wrote and wrote and still and just kept writing and writing and writing. I could hear the sound, right, the pen or pencil, touching the papers on the student desks. So just keep writing and writing, writing. So we wouldn't have time to just communicate or interact, right? But with the lecture notes here, I'm glad that you guys are not too busy taking notes, and so you can answer my questions, and that's good. Okay. All right. So now the general solution of this differential equation, right? The star has two parts. So it's just I'm just repeating the complementary solution, y sub c, right? And then the particular solution of this. Okay. So that's just repeating. Okay. So instead of using all the D operators, now we use the L. Okay. So section 4.1 is all terminology. So now let's talk about linearly dependent or independent functions and also solutions. Because that each solution that we get from here is going to be a function. So we may have more than one solutions combined. Okay. So if you put them together, we want to know whether they are linearly dependent or independent. So the question is, what does that mean, right? So what does that mean? So here, so if I give you a set of functions, column f1, f2, dot, dot, dot to f sub n, okay? So these functions right here are linearly dependent, okay? Linearly dependent. So I just want to make sure that I like to use the color in order, okay? Okay, so what does it take for a set of functions to be linearly dependent? The only way for this set of functions to be linearly dependent is if you can come up with some constants, okay? So that when you multiply them to the functions and add them up, you get zero, okay? So if you can come up with some constants for these to multiply to these functions and add them up, you get zero. Now, for those of you who already took linear algebra, which is math 79, you know what I'm talking about, okay? That's like linear combination, right, of functions. Okay, so for example, let's find out what that means. So let's say, for example, you have a set of two functions, and I ask you, are these two functions linearly dependent? Then you ask yourself, can I come up with a number so that when I multiply to the first function and come up with a number so that when I multiply to the second function and then I add them up, I get zero. Now, of course, you don't want to use zeros for all the c's, right? Because if you use zeros for all of them, then of course the left-hand side is equal to the right-hand side, okay? So that's why right here, you see, you have to make sure that you can come up with some constants for these, and not all of them are zero, okay? You can use most of them zero, but not all of them. So what is your guess here? What do you think you can use? So you can put a number here times f sub 1 and a number right here times f sub 2, where f sub 1 and f sub 2 are these two functions. And then when I add them up, I get zero. In other words, what times x sub 2 plus what times x squared, I'm sorry, and then 3x squared, and we get 0.
3 and negative 1.
3 and negative 1. Okay. Anything else?
And negative 3 and 1.
Yeah, so there are more than one possibilities. Okay, so in this case, you can say, all right, I can use 3 and negative 1, or since I already put a plus in between, so let's use this 1 and 3, negative 3 and 1. Okay, so yes, if you do that, then you get 0. So that is going to be a true statement. So you were able to come up with those two. So in this case, therefore, we write f sub 1 and f sub 2 are linearly dependent. Okay, so you think this is easy? It is not, right? Because if you have more functions, you have to play around with numbers. Okay, but what if you know what if I mean and I give you like 5 functions or even 10 functions, and those are not actually linearly dependent, and you just sit there and try to come up with 5 constants, and none of them will work, right? No, that's evil. Okay, so there has to be a better way, right, to determine whether these functions are linearly dependent or not. Okay, but this is one way of determining. Okay, now, or here's another way for you to figure out. So, or you can write like this. Okay, so I guess so instead of like up here, so instead of trying to find a bunch of constants so that when you multiply to the functions and add them up, you get 0. Another definition of linearly independent is the following. Okay, so instead of that, okay, we can say or if you can pick one of these functions and you can express that function as a linear combination of the rest. In other words, you take one function and see if you can write that, you can come up with that function by using the rest of the functions with some constants multiplied to the functions and add them up. So we call this a linear combination, okay? So if you can write one function as a linear combination of the rest, then we say that these functions are linearly dependent, all right? And it doesn't have to be the last function. You can just pick any function. You can say, you can try, all right, I'm gonna take, oh, by the way, some typos right here. I'm missing the subscript. So this is f sub 3 and this is f sub n. So please correct that for me, okay? So you can just pick any function and write it. All right. So, for example, right here, I give you 3 functions. Can you pick one of these 3 and see if it is equal to a linear combination of the other 2? What do you do? There are several ways. There are several ways here. You can just pick any function. You can express the f sub 1 as a sum or a linear combination of these 2 functions. Or you can say this function is a linear combination of these 2. Or this one can be written as a linear combination of these 2. So if you can do that, then these 3 functions are linearly dependent. Okay, so here, let me show you. So You see,
Second
f.
function is already a linear combination of the other two, isn't it?
What is that?
The second function is already a linear combination of the other two.
Oh, yeah, it looks like it is already, but you need to come up with with the constants, right? That you multiply to the other two functions. So okay, so let's do what Michael says. Okay, so you said f sub 2. It looks like it is a linear combination of I'm going to use c sub 1, f sub 1 plus c sub 2, f sub 3. All right, so now you need to tell me what c sub 1 and c sub 2 are. So what do you think? Now on the left hand side, f sub 2 is 2e to the x plus 5x. So what does c sub 1 have to be, and c sub 2 and c sub 3 has to be, I'm sorry, right here, it should be supposed to be c sub 3, okay? Okay, c sub 3. So that you know you're gonna get a true statement. Now remember, f sub 1 is e to the x, and f sub 3 is x. So what do you think c sub 1 and c sub 3 are? It's very easy to tell.
2 and 5.
What is that?
2 and 5.
2 and 5. Okay, you should say, if I ask you what should c sub 1 and c sub 3 be, right? You say 2 and 5. Okay. To say it properly, you say 2 and 5 respectively. Okay. Because that means I mentioned what I asked you what should c sub 1 and c sub 3 be. So when you give me two numbers and you say respectively, that means the first number that you just said is for the first constant that I mentioned. Okay, so you said 3, you said 2 and 5. Let's plug it in. So c sub 2, c sub 1 is 2, and c sub 3 is 5. Did you get a true statement? Yes, right? They're equal, right? Okay. So what does it tell you about these three functions? So what does it tell you about these three functions? The functions. You say f sub 1, f sub 2, and f sub 3 are linearly dependent. Okay. Okay, the third one. If the only way for you to get this combination right here to be 0, okay, like this up here, like by the definition, it says if you can get a combination of these functions to be 0 where all of the c sub i's are constants, but not all of them are 0, then we say these functions are linearly dependent. Okay. However, now the next definition says if the only way for you to have this being equal to 0 is when all of the constant c's are 0. That's what it means. So the only way for you, if the only way for you to get the left-hand side being 0 is when all of the coefficients are 0, then we say the functions are linearly independent of each other. All right, so make sure you know the difference between linearly dependent and linearly independent. Okay. Let's talk about Wronskian. So what is a Wronskian? By definition, if you have a set of functions, say f1, f2, f3, all the way to f sub n, then by definition, the Wronskian of these functions are defined as, so you write capital letter W, okay, of this set of functions. So the Wronskian of this set of function is defined as this, where the first row is just the functions. The second row is the first derivative of the functions. And you continue to do that until you get to the last row. And remember, the last row is one less derivative of the number of functions. So let's say if you have like 5 functions, then the last row is going to be the 4th derivative. Okay. And I see another typo right there. See this one right here is supposed to be n, right? Not 3. Okay, so you see, as I'm doing this, then I can I can spot some typo that I need to go back and rewrite. So that, oh, okay. Do you see this? Do you know what this is? Like the symbol right here? What is that?
Derivative?
What is that?
Derivative?
No, I mean these 2 vertical bars.
Determinant.
Determinant. Okay. So that is the determinant. So I hope you guys remember how to evaluate a determinant. Okay. So next, definition. So here's one way for us to define linearly independent set of functions, right? Here is another way, okay? The set of functions f1, f2, all the way to f sub n is linearly independent if and only if, so it goes both ways, okay? If and only if the Wronskian of those functions is not 0. In other words, these functions right here are linearly independent if the Wronskian is not 0. Okay, or let me say this. So the IFF right here is the if and only if statement, which means it says if these functions are linearly independent, then the Wronskian must not be 0. Okay, or the Wronskian is not 0. Or we can say if the Wronskian is not 0, then these functions are linearly independent. Okay, so it goes both ways. So if your major is in engineering, in math, in computer science, you have to be really logical and good at analyzing if-then statements. Okay, so from here, so this is what it says. So if this set right here is linearly independent, then the Wronskian is not 0. So you can reverse it and say, if the Wronskian is 0, then the set here is not I wrote it wrong again. Okay, so here's another typo, you see. Okay, so if the Wronskian is 0, then the set here is not linearly independent. Do you agree? Because you are negating the statement. Okay, so if the Wronskian is 0, then this set is not linearly independent. But if it is not linearly independent, that means it is linearly dependent. Okay, I don't know. Okay, so here it says if A, then B, right? So let's say if that statement is true. So right here, if I study a lot, or let's say if I have been doing my homework a lot, then I will do well on the test on Wednesday. Okay, so what is the negation of that? So when you see that symbol, it says, if I do not do well on the test on Wednesday, that means what? Then that means I didn't do my homework a lot. You see? So that's just a negation. So I'm just using this cell right here. If the set of functions is linearly independent, then the Wronskian is not 0. So if the Wronskian is 0, see, you negate it, then the set here is not linearly independent. So if it is not linearly independent, that means it is linearly dependent. Okay, so that's what it means. Whew. Okay, so why do we need this node? Well, because when I give you a set of functions and I ask you to determine whether the set is linearly dependent or not, you can just find the Wronskian of the functions and you can tell. Okay, you can just find the Wronskian. If the Wronskian is not 0, then you know that the functions are linearly independent. If the Wronskian is 0, then you know that the functions are linearly dependent. You see? So you can use the Wronskian to answer both. But sometimes when you run into functions like these right here, okay, and you are good at numbers, it's better for you to do it this way, okay, to get the answer more quickly. Now, if you got really stuck and you cannot come up with numbers for the C's, then you can use the Wronskian, okay? So there are options right there for you. So let's look at number 16. So I'm gonna try to save time instead of switching back to the textbook that I have in here and show you the problem. I expect you to have your textbook with you. So I'm gonna open my textbook to find out what the direction is for problem 16. So I want you to do this so you know, so you can learn this actively.